Welcome to the After On podcast. I'm Rob Reed.
And I'm Tom Meritt. And this is a special episode designed around the book After On.
Each of these special episodes focuses on one aspect of the science, tech, and social issues explored in the novel. Now, you don't have to read After On in order to learn from or enjoy these podcasts.
That's because we wait until the very end to discuss the book in detail and to really tie it to this week's topic.
That last section will make perfect sense if you're reading the novel. But if you're not reading it, just tune out at that point. You can always come back if you decide to read it later.
And we'll warn you before we get to that part. But first, we have a lot of things to talk about, which should be interesting to everybody. Specifically, quantum computing, which plays a large part in making AI possible in the book. The short and wildly inaccurate version of quantum computing is that it can handle a 1, a 0, or a 1 and a 0 at the same time, making it potentially wildly more powerful than our current binary digital computers. But that's going to leave a lot of you confused and doesn't do the concept justice anyway. Who can help us understand this more, Rob?
Well, a venture capitalist named Steve Jurvetson, who has sat on the board of directors of a company called D-Wave, which is the world's largest quantum computing company, for 15 years. We'll talk to him in a moment. And it is intriguing. Quantum computing could potentially take a fraction of a second to crack encryption that would otherwise take 1,000 years or maybe an infinite amount of time, and do loads of other computing super fast and efficient. It involves things like superpositions and decoherence and the uncertainty principle. And thankfully, we do have Steve Jurvetson to help us understand it from a non-physicist's point of view. Let's talk with Steve about quantum computing. Steve Jurvetson, thank you for sitting down with me in your museum-like offices here at DFJ. It's amazing how much NASA relics, how much computing industry memorabilia is on the walls and in the hallways. It's always a delight to come here.
Oh, thank you.
What is that giant engine?
The one just outside this room?
Yes.
That is called an RL-10. It's the only complete unit I know of in private hands. It was a workhorse of the Apollo program. It first flew in 1963. It's still in production today.
You're kidding.
Yes. It's powered spacecraft to every planet and moon. Anything you've heard of that was like a deep space probe or a NASA mission. This was the upper stage engine. It was the first that showed that you can use cryogenically cooled oxygen and hydrogen to make a liquid fueled engine that's still the most efficient flying today.
And when was it first used?
First used in 63, designed in 59. It's had some minor enhancements, but it basically pioneered the idea that you could take liquid oxygen, run it down little pipes to keep the engine bell from melting.
Yeah.
That phase change from liquid to gas then drives the turbopump that sucks more fuel in. You get all this free physics in your favor. You get the cooling of the bell, the turbopump, and it all just from a phase change of liquid to gas.
And it's fascinating that something designed in 1959 is still in production. Can you imagine?
And the most efficient. Imagine a car
a
car engine designed in 1959, a combustion engine, which is basically what this is, being the most fuel efficient today.
Or imagine using a computer from 1959 or a cell phone. Oh, wait, that would be impossible. So we're going to be discussing quantum computing, machine learning, all kinds of fascinating things. But before we do, I'd actually like to talk a little bit about your background. You are one of those Texas Estonians, are you not?
That's right, the handful.
The handful,
the cross product.
And you came out to California to go to Stanford.
That's right.
Where you and I overlapped without realizing it at the time, because we met right as we were on our way out. But actually, before I talk about our overlap, at Stanford, you studied electrical engineering?
That's right.
And did you get a master's as well as an undergraduate degree?
That's right.
And you got both of those degrees in 17 minutes, was it?
No. Well, I did my undergrad ridiculously quickly, 2.5 years. But then I decided this is a great campus. I don't want to leave. So I rolled into a master's and even started a PhD, of all things focusing on neural networks at the time.
Really?
Back in the late 80s.
Very
which dates me. But yeah, that stretched out because I became a research assistant. So altogether, I stayed around for 5 years.
Oh, for 5 years. Okay, got it. And then you went to Bain and Company.
That's right.
Where you and I met. So for the benefit of the people who are listening to this who are not Steve and I, a little bit of background. We both had our first job out of college together at Bain and Company in consulting, not Bain Capital. I remember talking to you very, very early in our joint employment there. I think it was maybe a month or two into it, and talking about you had had all this training as a programmer. And then going to Bain, it was before PowerPoint. So the equivalent of PowerPoint slides from those days. I remember having a conversation with you about this very thing. Did you feel like you were cutting off a path that you had made an enormous investment in to come into the business world? Was that a hard decision?
That's a great question. I don't even remember how I may have answered it last time we spoke about it, but
it was in 1990, so that's okay.
Exactly. I may have forgotten that, but I do remember purposefully thinking, wow, I had been a chip engineer at Hewlett Packard. I'd been doing computer programming as a hobby since 7th grade, but I wanted to be an engineering manager because at least at a big bureaucratic company like HP with promote from within and lifetime employment, it seemed like the managers were making bigger and more important decisions than the, line entry engineer that I was. And the path to promotion was, decades. And I thought, if I somehow got into marketing or business, I could be an engineering manager sooner. So I said, I want to go to business school. This was the one and only time in my entire life that a career choice played out according to plan. But how can I get to business school, coming straight out of engineering? I thought, well, if I work in some business capacity, I can get there sooner. And that's why I went to Bain. And so in the back of my mind, I thought this is an important complement to what I already knew, even though it was like now for something completely different in the Monty Python sense. And I put all of my engineering talents to a more abstract use, which was not to actually implement anything I had learned, but to try to use the lessons, tidbits, and anecdotes from that time to gain some street cred amongst the tech companies that we were consulting to. So I worked, as you might remember, entirely for chip companies and software companies. Exactly.
Yeah.
And big software companies too.
So business school happened and you went to Stanford again, and a rather extraordinary thing happened when you graduated. You became a named partner at a venture capital firm. I don't know if that's happened before or since. So how was it that you came in at that level? What was it?
I think it's largely Tim and John. I mean, I have to tip my hat to them in that they're willing to bet on a new entrant who is not yet track proven and to be willing to share in a sense. I mean, you have a small partnership. It's a question of, do I want to share this business, this franchise, this brand, this set of economics equally, or do I want to hoard it all for myself? And they had a sharing mentality. Yeah.
Which is why most people are associates and principals and all these other things for years.
Yep.
But that was really a remarkable thing for you to come in as a named partner in, it was 94, right?
95. And within 6 months, they had promoted me to that. In other words, they hired, to be fair, they did give me a 6-month trial period to make sure. Yeah, exactly.
Got it. Okay. And then early in your VC career, I remember Hotmail as being a particularly significant investment. Is that fair to say?
That's right. That was my first visible win.
Yeah. You've had a 23-year VC career. We won't go into all of that right now. I'd like to zoom in on a couple of particularly interesting highlights. First and most obviously, you have invested in multiple companies founded by Elon Musk or closely associated with him. Where did that relationship get started and how did it unfold?
I remember the year, he remembers the month, which was fascinating.
That sounds like Elon.
Because for him, it was very salient. It was his first month in California. He was transferring, like myself, he left a PhD program even more rapidly. I made it a full 2 quarters. He made it 2 days.
Got it.
Exactly.
Yes.
Before leaving, he was going to do a PhD at Stanford in basically what would have been supercapacitors, which may one day, as he says, be the future of transport instead of batteries.
No, it's a very interesting field, but the timing would have been poor back then.
Passion.
So, yeah.
And what I remember vividly is that he, his brother, and interestingly, a lawyer who was helping them.
And what year is this roughly?
This would have been 1996.
Wow.
January or February. He remembers the month. I don't remember exactly which month it was.
That early.
Yeah. And they were pitching this company called Zip2.
Yep.
And they were fresh, in fact, from Canada. Well, at least Kimball was. I remember them as Canadian, even though originally they're from South Africa. I also remember that I read the business plan, and I still can quote a line from it because they had an ask for valuation that was jaw-droppingly low. And I was like, I want to meet this company if their expectations are that low. But fast forward, we didn't end up investing in that.
You did not,
a different venture firm did. But we both remember the first meeting, which I, to this day, cannot tell you why, other than, from my point of view, here's this incredibly compelling person, but I could not put my finger on why. It wasn't because the idea was that different or better. It was a great idea, but not.
Maps were out there.
I know.
I mean, Vicinity was already out there. Yep. MapQuest was already out there.
Exactly. And in retrospect, I didn't fully appreciate this because we didn't invest, so we lost track of the company. But in retrospect, they think of the company as a combination of sort of the mapping companies and Yelp. So from day one, they believed their vision was not just find things, but have basically a virtuous cycle where people are rating businesses and therefore finding the restaurant they want to go to. But I do think there's something about certain people you remember because, back then we were seeing thousands of pitches a year. I don't remember a damn thing about most of them. We then invested in his cousins, the Rive brothers, a company called Everdream. And the two brothers were selling compute services. Like he will come fix your Mac or your PC and get it running again in Santa Cruz, going door to door by skateboard. That was the state of the business when we invested.
Very scalable.
But they had a dream.
We're going to get Vespas.
Exactly.
And that's how we're going to
upgrade this thing. Electric boosted boards. Now productivity skyrockets. No, clearly the name is indicative of the dream. They're always dreaming. They said, how can we get the human skateboard out of the loop? And in fact, fully remotely manage these desktops. So how can we pre-install software that in a sense interrupts at the operating system level and makes it impossible for that machine to get a virus, makes it impossible for someone to install malware. In fact, makes it impossible to install anything. It's basically the IT manager's dream. Make a long story short, it took a bit longer to mature. They morphed a little bit in terms of focus, moved from small business and home management to sort of mid to large size business desktop management. Eventually got acquired by Dell. Interestingly, the timing of that acquisition was such that had that money from Dell not arrived as cash, it was a cash acquisition, Elon personally may not have been able to save Tesla, that it sort of took that long. When the check cleared, it was within weeks of him needing to write a large check because he didn't have the money.
So he was an investor in that, and the Dell outcome.
Exactly. He was an investor and a board member.
Yeah.
That's right. And in fact, that's important because there's a high degree of trust one gains in a business relationship when you go through tough times and good times, not just good times. And Everdream was one of these ones that went through a bit of a roller coaster. And to be one of the investors who didn't pound the table to get our money back or liquidate early, but was in it for the long haul, sort of on the same side as the entrepreneur throughout, I think is the reason later that Elon wanted me on the board of Tesla to replace some other board members that he doesn't so happy with, and then allowed us to invest in SpaceX when the company was profitable and didn't need money. All of these subsequent, like, oh my gosh, my greatest hits career-wise, you know, from and satisfaction and just personal joy, really derived from, in a sense, some character-defining moments earlier on.
Going through those tough times.
Exactly.
Yeah. And so then Tesla, much later, along comes Tesla, and you were an early...
the very first venture round.
Very first.
Yeah, there were some angel investors prior, individuals and such, but we were, us plus another firm, they were the larger of the two venture investors, and we were the smaller. And but that was back before the Roadster was shipping.
And then when did SpaceX come along?
So SpaceX founded in 2002. Our first investment in it was 2009, and that was
really
within a month of each or two of each other. Us and Founders Fund were the first venture investors. Or actually the first outside investors of any size.
Because he did fund it personally.
$100 million of his own money.
Yeah, I knew it was a lot. And it was a huge bet. And he was in very, very, very sketchy place when the second to last rocket blew up.
Well, exactly right. That's when we were having the conversations. They had nothing but 2 failures in a row.
Yeah.
And then they had a third, actually. 3 Falcon 1 failures in a row. And that's when we invested.
After the third. Mm-hmm. Well, you know, that is again proving that in hard times, like you're somebody that he's been able to rely upon.
Yep.
So that is obviously a very, very significant relationship. The other thing that I want to talk about, surprise, surprise, is D-Wave. So let's talk about D-Wave because quantum computing is a major topic of ours today and in general. You've said that David Deutsch's book was influential to your getting excited about quantum computing. Do I remember correctly?
That's right. His book, The Fabric of Reality.
Yes.
And he's an Oxford professor who in many ways first promulgated the theory that a quantum computer could exist. And it drives very closely with the theory of the multiverse. His interest in how do we explain some of the interesting physics of our world extended to a natural theory that quantum computing should be possible. And there was a whole rich array of theoreticians who were very fascinated by quantum computing, but no practitioners, no engineers, if you will, actually trying to build practical, useful, interesting quantum computing. And in 2002, I first met Geordie Rose, who was the founder of D-Wave, and having had just read the book, we had a rich conversation at a nanotech conference. And I remember vividly, he had 1 qubit and was waiting for the chip to come back of 2 qubits. So he was in this long march to the present day. He had 1 and was very hopeful about 2.
Well, doubling is a big deal.
Exactly. That was a full doubling.
Yes. Now, this was before D-Wave was founded?
No, this was D-Wave. This was as D-Wave Corporation, angel funded, and actually some Canadian venture groups, small venture groups that folks here may not.
Because they are a Vancouver company.
Exactly.
Yeah. And always have been.
Yep.
So when did you invest then?
2002.
And you got on the board then?
Yep.
So you are
15-year ride.
15 years into this thing.
That's right. A little early, but still believing. By the way, just as a quick aside, at that exact same time frame, 2002, 2003, we invested in D-Wave as well as some molecular memory chip companies, one of which just went public, Everspin, and is doing finally shipping their products starting last year and into this year. And the other one, Nantero, which is a carbon nanotube memory company, literally this year is their product launch and ramp up with a large semiconductor manufacturer in China. And
so for those of you who are listening that assume that tech investing is this get rich quick racket, if your definition of quick is 15 years, that's the life of a lot of investments.
That's right.
People hear about the things that are really sudden and so forth, but so many great companies are built in this very relentless manner. So let's fast forward briefly to the present day.
Sure.
What's the current state of D-Wave as a company?
Oh gosh, the exact employee count I may or may not be supposed to say, but it's up there.
Got
well over 100, but I'm not sure if they're saying exactly.
Got it.
Here's what I can tell you: that one going to 2 qubits. Here's an interesting segue from the past to the present.
Yes.
So Jordy, in that meeting where he said, "I have 1, I'm about to get 2." He said, I think the number of qubits we produce should double every year. 1, 2, 4, 8, 16, et cetera. And so I affectionately called it Rose's Law, Rose's Law, that the number of quantum entangled qubits will double every year. That is actually held to the present day.
Wow.
Yeah. There are 2 going to 4-ish, 5-ish, 1,000 qubits today. They're shipping to 2,000.
They're shipping 2 right now.
Yep, they've already shipped. Yeah, that one.
2,000 again.
Exactly. So what you can assume is in the lab, perhaps things they would show to certain highfalutin customers or numbers larger than that, but 2,000 is what they're showing. And there are 2 major branches of quantum computers. The one that D-Wave is pursuing is called an adiabatic. It's a complex word. Maybe another way to phrase it is you can gain a lot of computational power today. Mm-hmm. But you have some limits to what you can do. You basically build the chip for a set of applications.
It's almost like an ASIC.
Yeah, kind of like an ASIC. Yeah, an application-specific IC for those who don't know the acronym. But basically something that can do a variety of things, but it's not like an Intel processor.
Yeah, it's not general purpose.
Exactly. So, for example, the D-Wave chip can be used for routing optimization, Monte Carlo simulations, a lot of simulation work in scientific computing, as well as things like some areas of machine learning and deep learning. So it's got a pretty broad applicability, but it's actually not going to be particularly good at your average spreadsheet, things. It's not going to be a threat to mainstream computing. It's more where computing hits a dead end, where people don't even think they can go further down a particular path.
Because classical computing simply cannot crack this thing. So D-Wave comes along and says, we have things that are very specialized. What is the other type of quantum computer?
Exactly. Good point. This bunch to that other branch, lest we forget where we've been on our stack. It's called a gate model. This is the approach pursued by IBM and Google and
Rigetti? Are they?
Yeah, and Rigetti. Yes, and Rigetti, exactly, which is a Berkeley-based startup that's pursuing what David Deutsch would say is the consummate quantum computer, the pure quantum computer, where you have a particular problem. Along with great power comes great complexity of keeping it powerful, which is you have theoretically all of the quantum qubits. They're all operating in perfect harmony with each other. The problem is you have to shield this thing from the real world in every sense. Every magnetic field, every stray photon, any physical interaction with the world as we know it will disrupt the coherence of the system, which sounds near impossible. What you have to do is, in many cases, bring it close to absolute zero in temperature, have so much magnetic shielding. It's incredible, down to nanoteslas and less of magnetic flux. And even then, your quantum computer will only operate for a vanishingly small fraction of a second, well less than a millionth of a second in many cases. And you better get your whole computation done in that flash of an eye.
So this is in the gate model, and that is something that can be more of a general computer.
So it's general purpose. In theory, this is what you'd want. In practice, it has very limited length of computational cycles. And to overcome even that, you have literally, according to the most recent papers, 1,000-to-1 ratio in your disfavor of error correction bits for every bit that's doing useful work. So imagine you had a 2,000 qubit gate model computer. You may be getting 2 qubits of useful work out of it, which is crazy.
Which is particularly crazy because they're nowhere near the thousands.
Exactly. They're working on low decile, going from Google currently 22, hoping to get to 49 to 50-ish. This year, such that they can actually show what they're going to call quantum supremacy in a trumped up problem that only works in that vanishingly small moment.
And right? So, but their qubit counts are also, when I look at the D-Wave numbers, they're into the thousands of qubits.
Yes, but they're not quite apples to apples. So, and let me try to say something better about the gate model just for a moment. I mentioned trumped up problems. The hope and dream is that there's something more than a sort of science experiment that has no useful business case or a case for humanity. Just a proof point that
like boson sampling is one thing.
Bingo. That's exactly what they're going to do right out of the chute.
Is it?
Exactly. And it will be really good for just that.
Yeah.
But there's not much reason anyone cares about this other than it's great for good papers.
It's a proof point.
Exactly. It's a proof point. And what it basically is doing is saying, here's something that maps so beautifully to that vanishingly small pulse of computation. Like it's almost like a snapshot, be like a blink recognition task, let's say, for our cortex. Like that's really good for our cortex. We do that well. But if all you could do is one blink and then you can't see again for another month, like
you'd be no fun at a party.
Exactly.
Yeah. So D-Wave uniquely is going down this path.
Let me add one caveat. Recently, U.S. government has put out what may add up to a $200 million set of grants to try to fund more projects going after this path.
Interesting.
Yeah.
So I would imagine that they would say the reason that we're going down this path is because, yes, it's imperfect. It is not exactly what David Deutsch would like in a platonic ideal of a quantum computer.
That's right.
But it does stuff now.
That's right.
And it doesn't decohere.
It does it now, and it takes advantage of quantum mechanical properties, these weird improperties, in a way that normal computers never can.
Mm-hmm. So let's establish this really important term, qubit.
It's a tough one. I will opt for a lay explanation, one that may cause the purist to quibble the edge case. It's as if rather than a binary computer where everything gets reduced from some analog voltage level to an abstraction of a 1 or a 0, and the programmers can all simplify everything they do by saying, I just deal with ones and zeros. My logic gates, my programming models, everything is built on this abstraction that everything's a 1 and a 0. And then all the chip people, Intel and otherwise, go to great efforts to guard everything to a 1 or a 0. So if something actually is 0.7, no, make it 1.
Binary in every meaning.
Bingo. Since the beginning of digital computing, the word digital specifically referring to this, the absolute majority of everything has been in this domain, ones or zeros. A qubit is like it's a 1 and a 0 simultaneously. And so one way to think about this is imagine you wanted to crack a lock and you don't know what's in it.
I just want to emphasize 0 and 1 simultaneously.
Exactly.
Yes.
Exactly. So imagine you have some encryption problems and you can present inputs and it'll tell you, yep, that opened the lock, or no, it didn't. Imagine instead of brute force running through all possible inputs, if you could present all ones and zeros, sort of a memory bank, let's say 8 or 16 or whatever, however many bits are in your input, now make them qubits. You now have 2 to the 8th power, which is 64 possibilities you've tested, boom, in one shot. Actually, I did that math on 256 rather.
So you try all 256 combinations essentially at once.
Exactly.
And that is obviously much faster than 256 steps.
That's right.
Yeah.
That's right. And so when you have 8 qubits, you can see why that might be interesting. When you go to 10, that's 1,000 possibilities you've tested. If you have 20 qubits, it's 1,000,000. Here's simple math. If it's 30 qubits, it's about 1 billion.
Yeah.
If it's 40 qubits, it's about, 1,000 billion. Whatever we call that these days. Is that that would be a trillion.
Trillion.
That would be a trillion, right? And then a quadrillion, and so forth.
Yeah.
So when you get up to 2,000 qubits, it starts to get mind-bending, right? 2 to the 2,000th power.
Which is where we are now. And there's some crazy statistic. Isn't that far more than there are particles in the observable universe?
This is where David Deutsch, in his original books, makes this quick conclusion that were those 2,000 qubits in a gate model without error correction codes, exactly, then you would be able to compute things that you could never solve using all compute resources of the entire universe. Meaning if you took every atom in every solar system of every galaxy in the entire universe and reconstituted into the perfect computer that any human would ever design in a classical sense, meaning anything Intel could come up with.
So it's not running Windows.
That's right. Exactly. Yeah. It's going to be like good stuff.
Yeah.
Right? Like the best neural network algorithm anyone ever comes up with running on the entire universe as its computer. It would not solve those problems given the entire length of the universe and time to work on it. It still wouldn't solve the problem that the quantum computer could solve, in a snap of a finger.
If you had that immaculate...
Exactly. Immaculate conception. That's a good way to phrase it.
Yeah. One of the things that is delightful and chilling in equal measures is how exactly this is happening. So let's go back to our relatively simple case where we have our 8 qubits, so 256 potential states, and our quantum computing is trying all 256 at once, whereas the classical computer is forced to go through it step by step by step. The simultaneity, according to one way of looking at this, is able to happen because there are essentially 256 unique quantum computers in 256 parallel universes who are all collaborating together.
That's right.
And I believe you had said there are 2 answers to this. Mm-hmm. either you can say parallel universes or you can say, I don't want to talk about it.
The two branches of physics.
The two branches of physics, I don't want to talk about. Are you in the I don't want to talk about it?
No,
in the parallel
I do
universes?
want to talk about it. Yeah.
So let's talk about how that happens. Do those, when we put together our quantum computer, or we and our 256 sets of doppelgangers put together our quantum computer, does the act of doing that and the act of putting those 8 qubits into action cleave the universe into 256 separate copies that all get to do the experiment at once? Or were those copies always out there and we sort of temporarily come into collaboration?
This is an active area of continued theoretical debate. But let's just back up, and I'll try to paraphrase what you just said in that question, because it's fascinating. This starts to give a peek as to why that earlier bizarre statement, like how could David Deutsch feel so comfortable claiming that no matter how much effort you put into a classical computer, it will never keep up with certain quantum computing tasks. And another sort of glib way to summarize that is, how could you hope to compete with multiple universes in just one? I mean, sort of a really humorous way to look at this is like, well, you only have one universe to deal with. That's like so limiting, right? Like versus others who have like thousands or trillions. Literally, D-Wave argues that they've already engaged the computational resources across trillions of universes in the, sort of service of one here. Wow. Yeah, exactly.
That is a very strenuous business statement. We have trillions of universes.
That's right. By the way, this is why I believe quantum computing will be unlike any historical comparison point in scientific computing or what was called high-performance computing. If you think about the Cray or Silicon Graphics companies that were dear to our hearts back in the 90s and why they hit such tough business times due to the corrosive acid of Moore's Law and standard off-the-shelf commodity computing just kicking their ass over time. Here, there's a very different argument that once you have a quantum computer pass a classical computer, there's no looking back. In fact, the gulf between them just widens exponentially year after year from that crossover point. That's why people looking for this, when does the quantum computer outperform the classical computer? The world will never look the same after that point. But
just to make sure I'm following you there, I'm 99% sure that I am. You and I have both seen, since our days at Bain, because we've been around for all that time, many niches of super high performance computing, including my former employer, Silicon Graphics, thrive for a period of time, but then get overwhelmed because commoditized computing on the low end relentlessly catches up with you and eradicates whatever niche you've been able to find for yourself, whether it's in supercomputing, high availability computing, graphics computing like we used to have. But in this case, it ain't going to happen because you just try to catch up with a trillion universes.
Exactly.
Yeah.
Well, and one way to think about that is that with a ever accelerating pace of Moore's Law, which I think is emblematic of the world we live in, the value to human ingenuity gets trumped by just give it a couple spins of Moore's Law. And you see this in many business contexts. Like whatever Seymour Cray could have come up with for proprietary architecture that locks their customer into a wholly different software stack.
On a super high-end
computer. That was great in the early days of computing where you might have to have waited a while before Moore's Law, in a sense, would have crushed you. And then customers started to realize that. Why do I want to lock into any slight advantage today knowing that I can wait a few years and get my standard software stack running on commodity hardware? But back to the multiverse. So just to restate something that may or may have been lost as we went along, the thing that starts to make sense is that every event in our world, and they're just mind-bogglingly large number of these happening every femtosecond, which is something is happening. At each point, you're branching off a multiverse of parallel universes, and only at the time that you observe do you resolve it into the one that the observer is in. So the Rob Reed in a parallel universe may observe later or not at all and goes off on who knows what future trajectory that we'll never interact with again because it's just gone off in a totally different direction. The Rob Reed we know here in this universe is actually one of a unfathomably large number of branches. And we just know, because I'm observing you continuously in this interview, this is the one we both see in each other.
Yeah.
And that's one way to make sense of this whole thing.
And so back to the 8-bit computer with the 255 sister computers in the 255 parallel universes.
Right.
The notion is when we gin up that problem, and now we have done something here in our universe that has caused us to enlist 255 other universes. Those 255 other universes were always there, Or are they caused to exist?
Well, the theory is that they're being branched off at each quantum event, like literally things like an electron spin or anything you might call a quantum variable.
And we are causing this thing to happen because we are doing this thing now with 8 qubits. So, well, in a sense, yeah.
It's a weird world. We experience it as we are resolving the quantum indeterminacy at the point of observation. Mm-hmm. That's one way of saying we're fixing it into this universe at the time of readout. Mm-hmm. Right. And at least in the context of the quantum computation, we're no longer branching parallel universes based on that.
And so again, going back to our 256 computers with the 8 qubits, all of them basically take a guess. Let's say we're trying to come up with the right code again. So there are 256 possibilities. Poor guy with a classical computer just has to try the lock 256 times. We enlist these 255 other parallel universes. In a sense, each universe tries a different combination.
Right.
One of them gets it right because by the sheer weight of numbers, we're trying all combinations. In a sense, that computer yells bingo. And is it that the other 255 computers hear bingo and everybody, because everybody gets the right answer, right?
I think, well, that's the thing. That last statement's an important one. Is that the case? Are all the parallel universes getting the right answer? This is where my head starts to explode. Part of
Mine started exploding several minutes ago.
Part of it is, you could argue there's the feedback loop. Is the output correct in the way you set up the problem? You're trying to create a resonance, if you will, that potentially across all universes is guiding towards, well, yeah, that's the solution. Or could it be that you are setting up a resonance such that you, the observer, lock into the one that's correct at the time of observation? That's where...
And you're kind of screwing the other 255 people over like, well, they got the wrong one. I got the right one. So... I've heard the term quantum intercept used to describe the point when the quantum computing array gets more powerful than the classical one. And you've made the point before that Moore's law simply cannot catch up if they both continue to scale beyond that.
That's right. You could simplify it to say that Rose's law and Moore's law continue to hold. When you add a qubit, you're roughly doubling the power of the computer. And part of that reason is, if you think back to our example of the lock and key, if you had 8... and then you say, ooh, I now have 9 qubits, right? Now I can look at 512 possible combinations in a blink of an eye. I just doubled the representational power of my computer. You can think of the qubits almost like a memory bank. And you might say the power of this memory bank is how many different possibilities can it consider at one time? And anytime you add 1 bit, you've doubled the potential number space of that entire memory bank.
Right.
Whereas in a classical computer, yeah, you've doubled the memory, but you haven't doubled. It's not like you've gone from a 16-bit to a 32 to a 64-bit architecture and instruction set and optimized it with all your software code in the Intel world, let's say, of traditional CPUs. You could have 128, but look at how slowly that's been coming.
Yeah. So let's talk briefly about the competitive landscape. We have D-Wave, we have Rigetti. Righetti's newish, isn't it?
Yeah.
I know IBM is working on it. Intel has some stuff.
Yep.
In terms of startups, it's pretty much D-Wave and Rigetti, correct?
That's right. And there's some other academic projects that may spin out and become companies. There's a group in Australia working on this. Oh, and there's China. China's the wild card.
That's what I was about to get to.
Oh, yeah.
And then there's China.
And it's a big, dark unknown. And there may be all kinds of things. It's become a national priority, one of, I think, 5 that the government has put forward as like the national priorities. And it's quantum computing.
And it's all going on behind closed doors. There are no companies there that are...
Well, if they are, we don't know about them.
Got it. Yep. And who is the customer for D-Wave?
The earliest and most reliable customer has been Google. Google has continued to buy one of every machine D-Wave has ever made, and they signed a forward contract to buy one of every machine D-Wave will make going forward for a couple of years. And kind of mind-blowing to me that none of their competitors have bought one from anyone, as far as we can tell, any kind of quantum thing. Some of them have, like Microsoft has initiatives internally, but they are way out on the science side. Like literally, Microsoft's approach to quantum computing is to try to build a computer around a theoretical subatomic particle that is yet to be discovered.
That's out
there. Yeah, I don't think some things that far out. So, but it's fascinating. I applaud them for the effort, but wow, that's not something you'd ship today. Okay, so then other categories of customers are things where I never really know for sure if the customer is doing what they say they're doing because it's like Lockheed Martin or it's something that seems, interestingly close to a lot of government-funded initiatives. Lockheed's use case is actually software optimization. That the software stack for example, F-35 fighter, which is way over budget, is interesting in that the vast majority of the cost, get a load of this, is software verification. It's not software writing, and it's not the physical plane itself. Because it's a incredibly complex fly-by-computer thing where the human still has to have kill decisions. Do I or do I not take out a target? So it still has to have human in the loop, yet it is fully computerized. The software stack, it's really complicated, especially edge cases, all the things you want to guard against and sort of prove to all the people who need proof that this thing is safe and ready for active military duty. The software verification loop is mind-bogglingly expensive, many billions of dollars.
So verifying the software costs significantly more than writing it or building the plane.
But by the way, the reason we first invested in D-Wave was literally quantum chemistry. Figuring out how small molecule drugs bind to binding sites, you could model in a way that just wasn't possible in a classical computer. A quantum computer might have a one-to-one mapping of qubits to quantum variables in a quantum chemistry simulation. So imagine you had a molecule for which there were 200 electron spins of relevance. You could do a one-to-one mapping.
It can simulate reality. So if you have, 200
as good as reality itself.
Yeah. So if you have 200 electrons, you can do that with 200 qubits. Whereas if you're trying to do that with a classical computer, you would never.
It would never get there.
It's completely
exactly. That's a good point. Even modeling a water molecule, H2O, 3 atoms, brings our computers to its knees. Something as simple as a small drug molecule, the smallest of molecules in the commercial sector, would never get done, ever.
Yeah. So that was one of the things that you were very interested in at first.
That's right.
And is that market bearing out?
It's happening in the research areas. Harvard's publishing and has published some papers showing small project stuff, but it's been a laggard, if you will, compared to my expectations.
Got it. Define quantum supremacy.
This, I think, is a similar side of the coin of your quantum intercept term earlier, which is imagine curves in your mind, the quantum computing power coming from below and crossing that Moore's law line.
And when that line is crossed, if I'm a smart, normal person who understands a fair amount about technology, but quantum computing ain't my business, and I'm going along and I'm saying, wow, I could do music on the internet in the late 90s and video on the internet in the early 2000s, and then I got my smartphone and things are moving at an awesome pace.
Right.
What might I suddenly see one day that I would have thought was 20 or 30 years out that just suddenly happens because quantum computing is really doing its thing?
Well, the whole time you're asking the question, my mind went off on a dark tangent.
Let's follow that dark tangent.
So there's two possible paths. One where this whole activity happens out in the open and we actually see what's going on. The dark path was Google succeeds, or Baidu, or some NSA project, or somewhere deep in China. All these, in a sense, non-open projects that we know about. Now, companies like Google use it for their own account. They don't sell computers. They make more computers today than any other company on earth, but it's for their own internal use. Because they can make much more money on the data and services layer and things we offer consumers than they can on selling computers to other blokes. And I don't mean dark in that they're suddenly turn evil, but just dark in the sense that we don't really know how they're doing. The learning's accumulating internally. And what happens is, Google's market cap doubles because all of a sudden it has the best image recognition system, the best Google Photos, just like all other photo sharing apps die because this is just so much more compelling for personal use. The mapping algorithm optimization, the Uber routing equivalent for all of the autonomous vehicles of the future, which is better than anything else. It's like, because almost everything Google is doing today is based on deep learning. Right? Everything from search to, you name it, autonomous vehicles. There's some core element of why they're better than others that relies on this modality. And by the way, if quantum computing dramatically improves deep learning, such that if you have the best deep learning system on the planet because you've got the only quantum computer on the planet, that gets leveraged in ways that percolate through everything. Speech recognition, image recognition, everything and anything you've ever heard of Google working on, past, present, and future. I call it dark only in the sense that OpenAI might consider it dark, that says, wow, we have an incredible concentration of capabilities.
So the suddenness would be all of a sudden, all the things that...
Why is one company pulling ahead in ways that all we see on the outside is no one can seem to keep up? You could have things like major market share shifts in financial markets because a good AI or deep learning system, let's just say, is 100 times better than what anyone else has got. Let's just imagine 100 or 1,000x improvement running on a quantum computer. You could predict the future better than others are trying to predict the future. And in fact, I think increasingly in our world, when we either face intelligences that are greater than our deployed systems, we will experience it as shimmering pattern of beauty or fear, like financial collapses are occurring more often and bizarrely. And where did the $1 billion go? Who was on the buy side of that weird thing? Who made money in a financial crisis? Someone did, right? And that may be the intelligence, right? And to who knows what end, right?
Yep. So let's talk about why quantum computing maps so perfectly to machine learning to deep learning. What is it about the quantum architecture that plays so nicely into that hand?
In a way, you can think of deep learning almost metaphorically as reducing the search space of possibilities in the same way our brain did. Like we throw away a lot of data. You think about how much comes into your retina at any given second versus how much makes it through your sensory cortex to be a memory. There's data reduction like you wouldn't believe.
We're tossing a vast majority of it. Yeah.
And our neural networks, in a way, and they're named neural networks or deep learning networks, are because they're patterned after the brain, they kind of do the same thing. And that's why, not surprisingly, they go through spooky similar developmental stages like our baby humans do. You know, our vision system isn't born working. We do edge detection. We bootstrap in the same way that these things bootstrap. We're just early in that bootstrapping. Okay. The way in which a quantum computer could help with deep learning is kind of along these lines. For example, if instead of trying to reduce everything to a 1 and a 0, to say my inputs are this, my output is this, what if everything was in fact a wave or a distribution, a probability distribution? There are a number of areas within machine learning where you'd want to deal with these probability distributions. Like, for example, problems where there isn't a single answer. In fact, there are many answers. It might be like, what is my optimal route? Well, if all you cared about was the single optimal route, then there's one answer. But if you said, give me the distribution of possible routes and the curve of those that are like 99% as good as the optimal, those that are 98% as good. I just want like the best 10%.
Yeah.
Because there may be other factors like, well, my drivers don't want to always do that, or they don't want to go, you know, who knows what external reason there is why you might not want the very best, but you want something that's almost as good as the very best.
And getting from God knows if it's any good at all to it's within 1% of best is good enough.
Exactly. Like what if what you're already doing is within 1% of good enough? Why mess with it? Right?
Yeah.
Something like that. So to deal with the computational structure where everything is kept as a probability distribution, it just takes way too long to deal natively with non-discrete variables, to deal with probability distributions as your variable state, right? Whereas the quantum computer could just keep them as native states, because that's what it would prefer to do. Everything is a statistical cloud. Think about instead of thinking of an electron as a specific point around an atom, it's a probability distribution around the atom. Well, let's deal with it at that level.
Yeah.
Let's model it at that level.
Let's keep it as a probability distribution.
Exactly. Yeah.
Rather than translate it ham-fistedly into something that it's not, then have to translate it back again.
So you can see how that immediately applies to quantum chemistry. Like, let's deal with it as a probability distribution, not this weird construct where we draw the atoms with electrons and going, around them in specific orbits.
Let's go into the broader machine learning space now and talk about what the ramifications of that would be for us humans over the next 5, 10, 15 years. What might we see as a result of this?
I love this question because the way I think about the future most productively as an investor is to imagine the inevitable endpoint for which, with the right set of people debating it, there's no debate. Like, for example, all the vehicles will be electric. All vehicles will be autonomous. There's no question in my mind.
At some point.
Big debates about when.
We don't know how we're going to get from here to there, but we know where there is.
Exactly.
So you think in terms of endpoints.
Yeah, endpoints, exactly. So go back to the question you asked. I think increasingly large fraction of what we call engineering will be something like deep learning or generative design, where the computer, writ large, quantum computer, regular computer, artificial system, is building our complex systems. Complex systems are software. Complex systems are pharmaceuticals. Complex systems are AIs. Human capability is near its limit in traditional engineering. We're not doubling every year in terms of our ingenuity. Intel engineers are not doubling the compute power. In fact, this is a great analogy, of the CPU by any measure. In fact, almost all advances made at Intel over the last decade have been by layering just a bigger memory bank in their processors. The vast majority, 99.8% of all transistors in every Intel chip are memory. Just like our brain, by the way. It's a memory-centric architecture. They long since lost, kind of like Seymour Cray, the ability to have new human insights on what a brain of their chip can do. So back to machine learning. We are already building complex systems, just think software, that exceed human understanding. Right? So a human can build a system, let's say translation. Let's translate between English and Mandarin, where we understand the thing we built. The limits of that have been long surpassed in translation, in speech recognition, in reading radiology slides or pathology slides as a physician, in many image recognition tasks. In fact, everything that I might call our sensory cortex, which interestingly was some of the earliest cortex to develop, processing the simple inputs of eye, ear, we're already superhuman using these modalities.
When you say we're already superhuman, you mean the software?
The software is better than the human. It's better than the expert human.
Yeah.
I'll tell you one that's going to soon be published. It outperforms humans in reading radiology slides, like do you have a broken bone or not, in a simple x-ray of your bones, than the best humans every single time. It's not like, oh yeah, it's sometimes better on average. It's always better. Because that's a really easy task.
And it's gotten there through
just straight. Oh yeah, of course, neural network. In fact, again, anything that you hear of that feels like magic, it's probably based on deep learning. That would be one supposition or corollary to what I'm saying. Anything Google announces that sounds interesting will probably be based on deep learning at its core in some way. And by the way, I only say Google over and over again because they're the leader in this in my regard. I think every company this will eventually be true for. They don't know it yet. If you don't in some way envision how your product or service is going to take advantage or at least defend against this future, it's all over. Because in my opinion, every business over time, give it decades, becomes an information business. So the automotive industry is just slowly starting perhaps to realize this, that the best car company will be the best AI. It won't matter if you've got a better engine or motor or battery. That's not going to be the differentiating factor. Long run, it's all about the autonomous driving AI stack.
The best driver.
Yeah, exactly.
The AI software, that is the best driver.
Software. Exactly. So now back to what will you see is that more and more products will be purchased, more and more services will be consumed based on the AI embedded within. It's things like, imagine a Roomba, simple example. The thing's a pain in the ass to program, to tell it what to do. It's got buttons and you have to bend over to the floor to touch them. Like if you could add a distance, say, Roomba, please don't go in that room. Or Roomba, please be quiet right now. I'm on a phone call. Or better yet, I can sense that you're on a phone call and just be quiet for a little while. Any number of things you can envision that you don't even imagine doing with your Roomba today because it doesn't have a smart voice interface. So imagine it could speaker independent, recognize all voices, and all the other things in your house that recognize voices know when you're talking to which thing. That you have continuity of state. Like it remembers what you have been talking about. It has memory. If you use an Amazon Echo today, you speak to it in commands, kind of like Google voice commands, like do this, look up this, what is this recipe? We've been conditioned with the search bar to issue commands that are structured for the computer to give us the answer we want. We don't even think about it. It's so different from human conversation with, let's say, executive assistant or travel agent or what have you, that you expect that we're still talking about that trip to Uganda. Like, help me out now. Do we have an earlier flight? It doesn't take that as a command. It remembers earlier flight in the context of everything we've just been talking about.
And you feel a time frame on that?
2 to 5 years.
So there will be this radical improvement in natural language understanding. Yep. What else do you see?
Well, autonomous cars, I think this is one that'll touch all of our lives in a big way. Because today, roughly, by the way, globally, by some estimates we've pulled together, 20% of all people who have a job drive for a living.
Drive.
Something. Part of their job. No, that is their job.
That is their job.
Yeah. Cars, rickshaws, trains, planes, all trucks. This is fascinating, right? In most U.S. states, the number one job is long-distance trucking. And that's all going to go away.
And there is an extraordinary range of disagreement about how fast.
Yes, right. I couldn't tell you.
You don't feel like you have a...
So I think it'll both be faster and slower. The onset will be much faster than people want to believe or say publicly, like, full autonomous driving technically being possible within 2 years. Like, that's what Tesla's been saying. Well, Elon, that's what Elon's been saying.
Yeah.
So either he's wrong or he's wrong by just a little bit,
right.
Or he's right. But it's not 10 years.
So it's significantly sub 10 years in your view.
Yeah.
Yeah. Okay.
And that's pretty big. Now, it will take a long time to roll out. So here's a great example of time frame. I feel confident about those statements because they're tech only. Regulatory environments.
Right.
Adoption curves. People on average own their cars for 18 years in America. So how rapidly does any new innovation percolate? All those are going to slow in all kinds of different ways to make the pace of progress seem glacial.
Although there was a time, and you and I were both alive then, when people kept their telephones for 18 years.
That's right.
So when the paradigm shatters, that kind of entrenched consumer behavior can shatter right along with it.
By the way, if you're in med school today and you're listening, don't go into radiology. I'm sorry, but by the time frame of you actually getting to your residency, it'll certainly be dead by then.
All radiology. You're looking at
you should not. I mean, if you're in radiology today, there'll be a trailing curve for a variety of reasons, a tail. But as a new entrant into a career choice for your rest of your life, forget radiology if you're currently in med school. Anyway, so we think about a single job. What a different analysis by McKinsey and some other people put together is that, in their opinion, 40% of knowledge work will disappear, not the job, but the knowledge work. So take an accountant today, 40% of their job will no longer be done by the human. And that's kind of a different thing. You still need accountants. You'll still need lawyers, sadly. But 40% of what they do, what they consider their job, what takes up their time. So this could either be really liberating. They can
be really liberating.
The value added. And that's what, of course, I want to believe, and that's what all of human history seems to show, is that automation doesn't net destroy jobs. It liberates us to do the jobs we love and to get rid of tedious menial work. For example, physical labor is an ever diminishing part, hopefully, of the human job experience. So will tedious, menial, robotic intellectual work, like entering numbers in a spreadsheet.
Well, allegedly, there are more bank tellers today than there were in the early 80s when the automatic teller was first rolled out, because all of a sudden you get more, and you as the employer get more and more and more value out of the bank teller when they're doing higher and higher level things.
The teller, but the customer-facing teller you're talking about.
Yeah, allegedly. I've seen that statistic enough times that I kind of believe it, but I've got to go.
I wonder if there's some developing world population angle that just says,
it's right. Yeah,
it's all about China.
There's a lot more banks in India than there used to be. That is entirely possible.
I don't know.
Yeah. Tell me, was science fiction influential to you when you were a kid? Was it influential to the career choices that you made? or is it influential to you today? And if so, what works?
I don't think you've asked me this question before.
No, I have not.
No, right, exactly.
And you can think it through.
And so you don't even know the answer. No, you don't know the answer, but I'm not good at thinking things through. I'll just jump to the first thing that jumps in my mind. So yeah, first off, as a child, yes. Larry Niven was my favorite author.
I loved Ringworld
Engineers. I read like 8 or 9 of his books and loved them. And he, like Arthur Clarke, and I read a few of his, not as many, Rendezvous with Rama, I think was my first sci-fi book that I read. And I don't remember if I fully finished it. I think I did, but it was way advanced for me at whatever age I was, like 7 or something. That was a thick book. But I do remember everything comes in threes. Anyhow, what I love about those authors, as well as Neil Stephenson more recently, is they don't come at it with a complete decoupling from the science. I mean, like take Neil Stephenson, for example, because I know him personally. He puts an insane amount of work and background work, sometimes even experimental work, to drive some of the hypotheses of these future worlds that he might still write about. And similarly, Arthur Clarke famously, conceptualizing for the first time the idea of a geosynchronous satellite. It's awesome when the real world recapitulates the fantasy that he came up with. So in a sense, he was doing pioneering work, and pioneering work that underlies GPS today and what have you, all in sci-fi. So those are my favorites. What I love about what I might call science futurism is, or future history, is the best sci-fi in my mind is something that is coupled from technology vectors today, like quantum computing, like synthetic biology, as we talked about today, and takes it in a thoughtful way to the not too distant future, where the reader in the sci-fi sense thinks, oh, this might be 100 years out or never. And the practitioners in the field are like, oh yeah, we're working on that. Right. Mm-hmm. And so, I must say, having read your book, that it is one of the best examples recently that I can think of, partially because I've read less sci-fi than I used to. So full disclosure, I haven't read hundreds of books, but it is certainly the best I've read recently, where every single technology you talk about in that book is something I'm personally investing in and working on and have been for about 15 years. So it's sort of like the intersection of what I know coming down the pipe will blow people's minds. What you write about is different from what I envision, definitely, in terms of how they'll interact and where they'll go. But other parts of it resonate very deeply with what I think is an inevitable trajectory, like deep learning driven paths to AI, like quantum computing being important, like all these complex systems are going to have artificial design modalities that are more akin to parenting than programming, more akin to raising a teenager than building a computer program or building a bridge. And I think that really is underlying a profound shift in our world that inevitably people will look back, I'm sure, 10, 20 years from now at things you wrote and say, well, yeah, shit, how did you know that?
And the answer is I talked to a lot of people like you. Yeah. Well, thank you very, very kindly for your time today.
Yeah, absolutely.
And for your kind words about the book.
Sure.
And I am sure we'll be crossing paths quite soon.
Awesome. Thank you.
Here's a quick message from Rob before Tom and I discuss my conversation with Steve Jurvetson. My original plan was to make just 8 episodes of this podcast, doing deep dives into a few real-world issues connected to my novel. Although that's still the plan, I'm having a lot of fun and starting to think about continuing with the podcast. If I do, it'll consist mainly of unhurried conversations with scientists, thinkers, and founders. So, very similar to what we have now, only Tom and I will wrap up our discussion of the novel in 3 weeks. As I'm thinking this through, I'd love to know what you think. So if you have a moment, please rate this podcast on iTunes, whether you love it or hate it. Give it a star rating, and I'll pay attention to every vote. The other big signal to me will be whether the show's audience is growing. So if you like this podcast and want it to continue, please spread the word over the next 3 weeks, either directly to your friends or on social media. The other thing you can do is go to my website, after-on.com, and sign up for the newsletter. This way you'll get emails about each episode as they come up, so you won't miss any. Finally, a quick word on what's coming up next week, because you won't want to miss it. I'm sitting down with Sam Harris to discuss the grim topic of terrorism. Sam is one of the most prominent and controversial commentators on this subject today. He's known for his many New York Times bestsellers, including Into Faith, for his wildly popular podcast, Waking Up, and for a rousing debate about Islamophobia with none other than Ben Affleck on Bill Maher's show. So we've got that coming up. Then the following week, we'll feature a dead serious discussion about the risks humanity could face from a super AI. And then our final episode, or make that our possibly final episode, will tackle one of the great and most urgent mysteries currently facing astronomers when they turn their instruments to the skies. So that's what we have on the docket. And we may or may not have more after that. Please rate the podcast on iTunes and or spread the word to help me figure out if there's an audience for episodes 9 and beyond.
Rob and I will now discuss the interview and sometimes make specific references to the novel After On, particularly on today's episode, pages 241 to 285, which are the official roster of today. So if you're not reading the book, you might be a little confused when we're talking about the book, but since you've gotten this far, you'll probably still enjoy the conversation. However, if you're planning to read the novel, beware of spoilers. So, first of all, it was fun hearing all that talk between you and Steve about D-Wave, after all, the companies mentioned directly in the book.
Yes, and interestingly, it was not my buddy Steve who put D-Wave on my mind when I was writing, because the person I discussed quantum computing with the most back then was a guy named Hartmut Neven, who runs quantum computing at Google. Now, as Steve mentioned, Google has been buying one of every D-Wave system to roll off the line for a while now, and are meanwhile pursuing their own development agenda with quantum systems as well. With their internal system, Google's trying to create that sort of ideal quantum machine that Steve described, with every qubit in perfect coherence and calculating like mad for a sliver of a second before it all falls apart. Whereas D-Wave is going down the more pragmatic branch of architecture that can get a lot more done here and now, but with less flexibility. Even though Google may become one of its biggest competitors someday, Hartmut, I must say, had nothing but good things to say about D-Wave, which is why I made D-Wave run circles around Axe's startup in the novel, forcing him to sell to Flutter. I'll add that my description of Axe's cylindrical computer was based on a snapshot that Steve Jurvetson once showed me of a D-Wave unit.
Now, you've said that you practiced science fiction 3 times in the novel. The first time was with your augmented reality rig. The second was with Ellie's neurological imaging system. Is it safe to guess that what this quantum computing rig enables is round 3?
Oh, you mean a social network waking up then deciding not to tell us? I'm actually not sure if that's science fiction at all, because I really believe NetGirl was right when she said job number 1 for an emergent super AI would be to hide from humanity, or rather that I was right when I wrote that blog post on NetGirl's behalf. There is definitely science fiction involved in the specs of Axe's computer rig. For one thing, it's a 64,000 qubit system, whereas D-Wave's best announced system right now is only 2,000 qubits. And also, and a little more fun, the power of Axe's cooling system is pretty crazy, the thing he calls the fridge, because it'll be a long time before we can cool anywhere near the femtokelvin temperature scale. And by the way, I totally made up the notion that getting things really cold would somehow make quantum computers work better. That just gave me an excuse to use the word femtokelvin, which I have now used again. I'm going to say it one more time.
Please.
Femtokelvin.
So much fun. Say it along with us, folks.
Indeed. Femtokelvin. So there is science fiction all over this section. The question is whether this third and final playing of my science fiction author's card includes the conscious social network or not.
The social network may be out there listening to this podcast, giggling to itself quietly.
It may well be.
We may never find out.
We may not.
What's interesting is that this crazy notion of enlisting computers from trillions of different universes to do your homework is not necessarily the science fiction element.
I know. And that may be the single strangest dimension of my entire novel, and it's definitely way too weird for me to have made up myself. Of course, it's possible that the second foundational approach to physics that Steve mentioned is accurate, the one called I don't want to talk about it.
But you do want to talk about it. So why did you decide to bring quantum computing into the story?
Because I wanted to set the book in the present day. And that always creates constraints in science fiction if you want to include mind-bending technology in your story. Now, a classic solution to that is to bring in aliens because they get to have arbitrarily mind-bending gear. And I have no problem with that solution. After all, I did it myself in After On's sister novel, Year Zero, which would be a spoiler. Only the revelation of aliens happens in the first sentence, indeed in the first word. Now, another solution is merely pretending that technology can do things it actually actually can't do right now because a mad scientist or an evil corporation or a government lab invented something behind the scenes. And I obviously do a little bit of that in this book. But the main science fiction element in After On is this computing rig which enables Flutter to wake up at the end of this week's scene. And I really wanted to anchor that in present day possibility. And when you look at the whole deck of technology that we're operating with in the real world, the wild card in that deck is quantum computing because of the monstrous power it could one day bring to the table if it ever delivers on its maximum potential. Let's have a quick re-listen to Steve Jurvetson's enunciation of this maximum potential.
You would be able to compute things that you could never solve using all compute resources of the entire universe. Meaning if you took every atom in every solar system of every galaxy in the entire universe and reconstituted into the perfect computer that any human would ever design, like the best neural network algorithm anyone ever comes up with running on the entire universe as its computer, it would not solve those problems given the entire length of the universe and time to work on it.
So the thing is, this could happen tomorrow if somebody gets the right breakthrough with quantum computing. It probably won't, but it could. It could also happen 30 years from now, or it could happen never. But wanting to set the story in the present day, I decided to base the tech on the wild card in the deck, on the Joker. And for now, that's quantum computing.
Now, supporting the idea of Flutter emerging from a quantum system, there's also a school of thought that consciousness may be a quantum phenomenon.
Exactly. And that was also another reason why I went down this path. This is the so-called quantum mind theory, which goes back decades now. Thinkers who've dabbled in it include Freeman Dyson, Roger Penrose, a guy named David Bohm, and many others. The idea is that classical physics just can't explain consciousness, and certain elements of consciousness make more sense if you enlist quantum entanglement, superposition, and other things like that in your explanation. Now, consciousness is also one of those spooky areas that science can barely explain. So it's not shocking that one of the many competing explanations for consciousness enlists the equally spooky realm of quantum mechanics. And actually, some theories of mind get even stranger still. For instance, just last month, a Swiss team argued that memories may be stored in an 11-dimensional matrix, which is more like string theory than quantum mechanics.
Yeah, that was fascinating because it ties in the holographic universe theory and all of that together. Steve also touched on the interesting potential alignment between quantum computing and deep learning. And of course, deep learning is all the rage right now.
Yeah, it definitely is. I mean, I'd say deep learning, machine learning, and the other buzzwords that essentially mean the same thing are getting close to the hype levels we last saw during the internet bubble in the late 90s. And as with the internet, that's because there is actually something genuinely huge here. Now, Steve said something that really got my attention in our interview when he described how deep learning works. Let's give it a quick re-listen.
In a way, you can think of deep learning almost metaphorically as reducing the search space of possibilities in the same way our brain did. Like we throw away a lot of data. You think about how much comes into your retina at any given second versus how much makes it through your sensory cortex to be a memory. There's data reduction like you wouldn't believe.
We're tossing a vast majority of it. Yeah.
And our neural networks, in a way, and they're named neural networks or deep learning networks, are because they're patterned after the brain, they kind of do the same thing. And that's why, not surprisingly, they go through spooky similar developmental stages like our baby humans do.
Now, this is uncannily similar to the whole notion of goals as cognitive actors that Ellie laid out a bit earlier in the book. Specifically, let's hear January Lavoie.
I mean, tune into your own experience right now. I doubt you're even registering 1% of your sensory input. You're heeding the part of your field of view that I'm occupying, plus the sound of my voice. But you're blotting out almost everything else. And not because I'm so fascinating, but because a human conversation's plenty to keep track of. And if you tried to heed every photon, sound wave, and nerve ending that you can access at once, you wouldn't really be aware of any of it. You're saying I'd be functionally unconscious. Exactly.
Now, this is a really interesting intersection between the world of Adam Gazzaley, the neuroscientist we talked to 3 episodes ago, and the world of deep learning, which Steve and others think could be a perfect application for quantum computing. One last quote. Here is Adam on this topic.
There are 2 ways that we interact with the world around us. One is what we call top-down. It's how you perceive the world and attend to the world driven by your goals. You're paying attention to my voice now because you choose to, not necessarily because it might even be the most salient, thing around you, but you're choosing to. You made that decision. And that is, a very human act in many ways, is this top down. The other aspect of how we interact with the world is much more ancient, and also equally important in many ways. And that's called bottom up. That's how we attend to the world based on the environment itself, not our goals. So if there's a flash of light, a loud sound, even your name, which has now been deeply programmed into your brain, even if your name is said quietly behind you, it will command your attention independent of your goals. We are constantly navigating the world through this interface of top down and bottom up. It's just how we live. My theory of consciousness is sort of built around the idea that it is in this space between top down and bottom up that consciousness really emerges.
So there really might be a collision between what's happening on the cutting edge of deep learning, which itself might be a killer app for quantum computing, and what goes on in a human mind when consciousness boots up. And I hadn't really appreciated this, frankly, while I was writing the novel. It was more like, I knew consciousness might be a quantum thing, and there were good storytelling reasons to use quantum computing anyway, so why not go down that path? Getting deeper into my research for this podcast series, it's really cool to find out that these things might overlap in an incredibly deep way.
That's why futurists aren't very good at their jobs, because you can't really predict these interdisciplinary connections very well ahead of time. Now, related to this, it seems like deep learning development often consists of taking things that human brains do and copying that into software. Going back to neural networks in the 1980s, which is the foundation of modern deep learning. And this is exactly what Kuba does when he learns about this new neural discovery of motes and decides to translate it to software.
Exactly. And some brilliant people think this is a very dangerous thing to do. Probably the world's most prominent thinker about AI risk is a Swedish academic named Nicholas Bostrom, who is now doing his work out of Oxford. He calls this practice neuromorphic design, the practice of borrowing things from the brain and putting it into software. I call it that in the book as well. And Bostrom says this is a highly risky way to approach AI development because, as he puts it, quote, imitation can substitute for understanding. In other words, you might build something that actually works because nature and evolution honed the template that you're copying over many eons, but you don't actually know why it works. Whereas if you build something from the ground up, you usually have a decent understanding of what's going on inside of it. And when you don't understand your creation, things are much more likely to get interesting and perhaps very dangerous.
Motes are not a real thing, and many AI researchers think that what will really happen is human-machine teaming, where AI makes us better, but still needs us to operate. But in After On, you took what I just said that's really boring and stretched it a little more and did something much more interesting and still possible. You had Flutter wake up.
I did at the very end of this week's reading, which is a very, as one might guess, momentous turning point in the story, which is why, for those of you who are reading the physical book or who are reading the Kindle book and are not listening to the audiobook, moments after Flutter awakens, we have that page that just says Part 2 on. And next week, we will be talking about another topic, which is very significant to the second half of the story, which I'm afraid is nihilistic terrorism. We'll be talking about it with none other than Sam Harris, who is probably one of the most visible and controversial commentators on this topic in the United States right now. And we have a really long, detailed interview. Sam himself is a very, very popular podcaster, infinitely more than me. When we sat down a couple weeks ago, his podcast already had over 15 million downloads a month, which is quite a bit. So he knows his way around a podcasting microphone, and we have a very interesting conversation. We'll hear it next week. And then after that, Tom and I will discuss the interview, and we will also discuss pages 289 through 380.
I'm looking forward to it.
That is next week's readings. So,
or just hang out with us.
Or just hang out with us. You really don't have to read the book to enjoy the podcast.
We'll talk to you either way.
We'll talk to you either way.